Okay, quick question. Why don't satellites just fall straight down to Earth? I mean, gravity's pulling on them non-stop, right? So what's the trick? Let's break it down. Fast. Imagine you're throwing a baseball. Throw it gently, it lands nearby. Throw it super hard, it goes farther, but if you could throw it so fast that as it falls, the ground curves away below. Boom! That's orbit. The satellite is falling, sure, but it's moving sideways so quickly that the Earth's surface keeps dropping away, and it never actually hits the ground. Here's where the numbers kick in. The speed a satellite needs to stay in orbit is called its orbital velocity, and it depends on how high up it is. The closer you are to Earth, the stronger gravity pulls, so you have to go faster to not crash. That's why the International Space Station zooms around at nearly 8 kilometers per second. Go higher. Gravity gets weaker, so you don't need to go quite as fast. The magic formula for orbital speed looks like this. VE equals the square root of gm over rg is gravity's constant, m is Earth's mass, and r is your distance from the center of the Earth. Basically, it's physics' way of saying, go fast enough and you'll keep missing the ground forever. But wait, getting up there is a whole other beast. Rockets have to punch through the atmosphere fight drag and give the satellite enough speed sideways to reach orbit. The higher you want to go, the more energy or power you need. That's why rocket launches are such massive undertakings. So next time you see a satellite gliding overhead, remember, it's not magic. It's just a perfect balance between falling and racing sideways, thanks to some wild physics. Stay curious and keep looking up. Let's dive deeper into that formula. V equals square root of gm over rg is the universal gravitational constant. 6.67 times 10 to the negative 11. Earth's mass is roughly 6 trillion kilograms, and r changes depending on your altitude. Closer means faster speeds needed. Low Earth orbit satellites like the ISS need about 7.8 kilometers per second. Geostationary satellites at 36,000 kilometers up only need 3 kilometers per second. That's why we have different orbits for different purposes. Getting there requires enormous amounts of energy. That's why rockets use multiple stages. Each one gets you a little faster. Fighting through atmosphere wastes huge amounts of fuel. The final burn gives you that crucial sideways velocity for orbit. The total energy involves both kinetic energy, half mv squared, and gravitational potential energy, negative gmm over r combined. The total orbital energy equals negative gmm over 2r. Rocket engines produce millions of pounds of thrust, burning thousands of gallons of fuel per second. To escape Earth's gravity well entirely requires 11.2 kilometers per second. But orbit only needs about 70% of that speed. Mission planners calculate every detail precisely. Computer simulations model exact launch windows and trajectories. Launch windows are often just minutes long for optimal efficiency. Today's mega constellations put thousands of satellites in coordinated orbits. GPS satellites maintain precise timing and positioning from 20,000 kilometers up. Weather and Earth observation satellites provide crucial data from various altitudes. Reusable rockets are making space access cheaper and more frequent. Future technologies like space elevators could revolutionize orbital access. Manufacturing in orbit takes advantage of microgravity conditions. Every satellite up there is a testament to human understanding of physics. These same equations you can learn and understand yourself. Next time you see those moving stars, you'll know the incredible physics behind them. Keep exploring, keep questioning, and remember, the universe follows beautiful mathematical rules. And now you know the secret of why satellites never fall down.